Okay, and the yellow one, as I have told you, we have to do some measurement. We have to get some measurement, basically. Resistor, inductor, capacitor, and voltage and current. Okay, voltage and current measurement. Then we have to take some. We have to see some signal measurement stuff. Okay, time domain and frequency domain signal measurement. Signal measurement. Okay, so these are the content of learning outcome one. Okay, so we are here. We are here in RLC measurement. Okay, for the RLC measurement, we are using bridge technology, bridge techniques. Okay, bridge technique. Okay, this is one of most popular technique. Okay, one of popular technique. Okay, there are other technique also to measure RLC, to get the RLC measurement. Okay, so basically we have talked about two types of bridges, AC bridge and DC bridge. Okay, I think we have discussed on the DC bridge. DC bridge use DC source. That is why it has that name. Okay, and we use DC bridge to measure only resistance. Okay, resistance. I think that is enough. Okay, so so we are talking about the balance condition, balance condition, balance condition. Okay, already talked about the balance condition. Okay, so if the balance condition is there, if we have a resistor bridge like this, okay, if we have a resistor bridge like this, if the DC source is connected to this terminal, the galvanometer or the voltmeter should be connected to the other terminals. Okay. The balance condition we can write R1 divided by R3 is equal to R2 divided by R4. Okay. And if one of this resistor is variable, and if you know other resistance, okay, so you can measure the unknown resistance using this setup and the balance condition. Okay. So there are other conditions also, non-balance condition and partially balanced condition. We are not going to talk about them. Okay. So that is DC bridge. Okay. So that our study may be for 1 credit module. This is it. Okay. So using Kirchhoff and Ohm's law, we get this result at the balance condition. Balance condition means this voltage is equal to this voltage. That means this galvanometer or voltmeter reading is 0. That is referred as the balance condition. Okay, maybe you can remember. Okay. So I think that is enough for the DC bridge. Okay, so that is very simple. Okay, and we will move to AC bridge. Okay, we will move to AC bridge. Okay, so AC bridge we can basically use to measure resistor. Also we can measure inductor and capacitor. All these passive components can be measured through AC bridge. AC bridge means we are using AC source, AC voltage source. Okay, AC voltage source. So that is why it has that name. Okay, AC bridge. Okay, so so if you consider the capacitor, it is somewhat like this. Okay, and if we connect a source, let's say that we connect a DC source here. DC source here. Let's say that this voltage is E or something. Okay, and this is the capacitor. Okay, we know that capacitance is uh, defined as C, that is defined as Q divided by V. Okay, V is the voltage across the capacitor and Q is the charge. Okay, so here in this side, the plus charge will be there. In this side, minus charge will be there. Okay, and Q divided by V, the capacitance is defined like this. Okay, C is the capacitance. Okay. So this is measured in farad actually. Farad. Okay. Farad means nothing but coulomb divided by voltage. Okay. The charges measured by coulombs, voltage measured by volt. Okay. So farad can be defined as coulomb divided by voltage. Okay. So you already know this. Okay. And also we know that Q is the total charges of this capacitor. Okay. And if you consider a current through this capacitor, okay, if you consider the current through this capacitor, I will put simple T, simple I. Okay. So that current will be changed with the time. Okay, it is not a constant. Okay, so you know that normally, so maybe you know that for the capacitor. Okay, once we have connected a source, DC source, capacitor is starting to charge. Okay. So time versus voltage. Okay, so capacitor is starting to charge. Okay, so charging will be like this. Okay, so charging will be like this, and this is the maximum charge. If this source doesn't have internal resistance R, okay, if the internal resistance is 0, that means if it is ideal source, this voltage will be equal to the battery voltage. Okay, so anyway, it will be a maximum voltage. Okay, okay, like this. To get the maximum voltage, it will get some time. Okay, so this is the charging time of the capacitor. Okay. And so you can see that here the capacitor voltage is changing. Okay, from 0 to maximum. Okay, so this this uh, this condition we name as transient state. Maybe we have learned these things. Okay, you know this. Okay, for our course, all these things are not needed, no needed. Okay, and this is we called as steady state. Steady state. Okay, so transient state, then steady state there. Okay, so you can see that the capacitor voltage is gradually increasing and it become a maximum value. Okay, so if we consider the current, through the capacitor, so current will be, when the voltage is 0, current will be maximum, then current will be gradually decreasing and comes to 0 when it get fully charged. At the steady state level, the current will be 0. Current through the capacitor will be 0. This is current. So you can see that current is changing with the time. Okay, current is changing with the time. And if you want if you want to calculate all these charge, you know what is charge, okay? You know the current, okay? You know the definition of the current. What is the definition of the current? That is the number of charges, um, across area at a unit time, no? At a unit time. Okay. So that is the charge rate that is defined as current, no? Flow of charge particle while moving through an electron conductor in space. It is defined as a rate, no? It is defined as a rate of flow of electric charge. That means the charge per 1 second, okay? Q divided by T. That is defined as current, okay? I, okay? So that is the rate of charges, okay? Cross area, okay? So if you want to, if you want to, if you want to measure this Q, what you have to do? If you measure this Q, the total charges, let's say that at T time, let's say that here this point is T. Let's say that this is T1 or something, transient is 10, okay? So at T, if you want to find the full charges, that means you have to add all these charges, no, all this current up to here. That means from 0 to T, if you integrate the IDT with respect to dt, you will get the total charges up to T, up to time T, okay? So you can use this definition, then you can write C is equal to Q. Instead of Q, you can write C equal to T IT dt, okay, divided by V, okay? Then if you can get V here, okay? So V is also a function of time. V is also changing with the time, you can see, okay? Vt, so I will write it Vt. I will write it Vt 1 over C, okay? So maybe you are familiar with this equation. This is the voltage. This is the expression for the voltage uh, at any t time, general t time, okay? This t can be any value, okay? So this is the voltage at t, that is Vt, okay? So you can find like this. You can integrate. You have to integrate the current to the capacitor with respect to dt from 0 to that specific time point, okay? And if this capacitor is already charged, okay? If this capacitor is already charged before you have connected it to the battery, if it is a used capacitor, it can be already charged, okay? That means maybe you are starting from here, okay? So it has already initial charge, okay? Let's say that initial charge is V0, okay? If it has initial charge, the V0 is there, and uh, let's say that V0, uh, so maybe here at the V0 point, that time is considered as t is equal to 0. Then it will be 0 to t. if you consider that time is t1 or something, so this will 0, it is not from 0, t1 to t or something, okay? So anyway, okay, so you can consider at v naught, that is the initial condition, v naught, at t is equal to 0. So you have to integrate this from 0 to t, okay? So I'm not going to much explain these things. I hope you have already learned this, okay? Okay. So this is one uh, equation for the capacitor. If capacitor is not charged, initially not charged, this V naught will be 0. Okay. And if you get the derivative of this expression, okay, then you have to derive this Vt by dt. So here you have 1 over c. If you get the derivation of this integration, okay, so it is integrate, you have answer. Then again, if you have derivated, then you will get the answer again it. Okay, so that is the current it. And this V naught is a constant, so it will be 0. And you will have this one. Okay, so you can get the expression for the current it. That is C dVt dt. Okay, so this is the expression for the current. Okay, this is the expression for the current. Okay, so these expressions are there. Okay, these expressions are there related with the capacitor. Okay, related with the capacitor. But actually we for our subject, this equation not much important, so you don't need to keep remember this. If you need, you can just write them, mark them, okay? If you need, and these are the capacitive discharging charging curves, okay? And maybe you can remember that if you have a resistor along this series resistor along this capacitor, we can write the equation. So it will be using this one or this one. Okay. So definitely that will be a differential equation. By solving that differential equation, you can find you can you can find the answer for this VT. Okay, you can find the answer for this VT. Okay, uh, so it is e to the power t RC, that kind of 1 minus e to the power TRC, that kind of uh, equation. I can't remember that one. Okay. So uh, that is not much important here for us. Okay. But maybe you can remember these things you have already learned. Okay. Maybe. Okay. Okay. So anyway, this is it. Okay. So if I okay, maybe you have learned that uh, maybe you have learned that uh, we can do some domain transfer. We can do some domain transfer. Domain transfer. Uh, this domain transfer is normally doing for analytical and modeling purposes. Okay. So maybe you have familiar with in signal and system. In signal and system, maybe you have learned this for the engineering mathematics also. These things maybe you have learned, okay? Engineering mathematics also, some domain transfer, okay? Uh, there are some domain transfer techniques, okay? So basically, maybe you can remember we are learning two type of transformation. One is Fourier analysis. One is Fourier analysis. Another is Laplace. Laplace transform or Laplace analysis or Z analysis. Laplace transform or Z transform. So in Fourier analysis, we can convert time domain signal into frequency domain. In Laplace transform or Z transform, we can transfer time domain signal into complex domain. Okay, so this is using Fourier transform time to frequency domain, and you can do the vice versa frequency time domain using inverse Fourier transform. Okay, so time domain to complex domain. This is complex domain. Okay, this X is a complex number. This is complex domain. Okay, so time uh, can be transformed into complex domain using Laplace transform or Z transform, and the same way you can do the vice versa complex domain to time domain using inverse Laplace transform or inverse Z transform. Okay, maybe you have learned this frequency Fourier transform and Laplace transform. If you haven't, don't worry. Okay, and if I get this equation, okay, if I get this equation, that is IT is equal to C dV T dt. Okay, if I get this equation, okay, so I am going to do this time transformation. Okay, so I just try to do a time transformation. Okay, let's say that I am going to transfer this time domain into frequency using Fourier transform. You can do the other things also. Okay, same. Okay, the same concept is there. Okay, so let's say that if IT is transformed into frequency domain, let's say that I omega using Fourier transform. Okay, and if VT is transformed to frequency domain, let's say that it is V omega using Fourier transform. Okay, and you can see that here you have a derivation. Okay, and this under this transformation, maybe you can't remember. Okay, you can't remember if you haven't learned them. Maybe for a long time, maybe you maybe almost forgot these things. Okay, but just try to get remind. Okay, this is just for the explanation. Okay, not no need to keep remember these things. I will tell you what you need to keep in remember. Okay, so these are just for your understanding. Okay, so don't worry. Okay, so um, so maybe you can remember that when we are doing this kind of transformation, we are using some properties. We are using properties. Properties in Fourier transform, Fourier series, properties in Laplace transform, likewise. Okay. So properties means that is some kind of special feature when we are doing this transformation. If we can see the common thing, it is normally considered as a property. Okay. For example, there are different type of property. Okay, maybe you can remember the convolution property. That is very popular. Okay, convolution property. When we are analyzing linear time invariant LTI system, we have to use this convolution property most oftenly. Okay, and uh, maybe you can remember that linear property. Linear property. Um, I can't remember all the properties. Okay, so there are some kind of properties. Okay, And there is a property called differentiation. Differentiation in time property. Differentiation in time property. That states that property means, okay, if we have a signal and if you convert it to Fourier transform, let's say that you have V omega, okay, and if you have a derivative of this signal in time, okay, that is why it is called differentiation in time, okay, dvt dt, okay, and if you get the Fourier transform of this derivation, you will get okay, you will get uh, Cj, sorry, you will get j omega, into V omega. Okay. So this, if you get the derivative, you will get this kind of result, j omega with respect to V omega. So now I'm going to turn this to frequency domain. Okay. Frequency domain. Then I have I omega. It is uh, transformed into Fourier domain or frequency domain. So that is I omega is equal to C is here. Now we assume that Vt, once the Vt is transformed into Fourier transform, Vt is transferred into frequency domain using Fourier transform, V omega, but here we have the derivation. So you will have j omega V omega. Okay, so you will have this. Okay, so now I will take like this. Okay, I'll just get the cross product and I will write like this: V omega divided by I omega is equal to 1 over C omega j. Okay, so I can get this equation now after I get the time transformation. Okay, after I get the time transformation. And what is this? Then what is this? Can you tell me what is this? So you know the Ohm's law, no? V equal IR. Okay. So if V divided by I, that is R. Okay. So if we get V divided by I, you will have a resistance. No, you will have a resistance. Okay. So here also, now you can see that here also V is in frequency domain, but it is still a voltage. Current is also in frequency domain, but it is still a current. Okay. So voltage divided by current, so it will be a resistance, no? Okay. So this will be a resistance, no? This will be a resistance. This will be a resistance. Okay. So what is this? The resistance means this is measured in ohms. Okay. So this is measured in ohms. Okay. So if we have a capacitor like this, okay, and the this is the resistance created by the capacitor, no? That is 1 over C omega J measured in ohm. Okay. So this is the resistance created by the capacitance. Resistance created by the capacitance. By the capacitor. Okay. This is the resistance created by the capacitor. That is measured in ohm. But it has a difference. This one and this one has a difference. What is that? What is the difference between this resistance and this resistance? Can you see it? What is the difference between this one and this one? This is also ohm, this is also ohm. But there is a difference between this resistance and this resistance. What is that? The difference is this J. What is this J? This J is the square root of -1. No? This is defined as J. This is the complex value. This is a complex value. No? This J is a complex number. Correct?
Yes.
Okay. So that is the difference. Okay. So what is the difference is that this one is a real resistor. This one is a real resistance. But this one is not real. It is imaginary. Imaginary. We normally call them complex resistors. Complex resistance. Complex resistance. Okay. So we are not using this resistor word here. Okay. We are normally using reactance. For the complex resistance, we are using the name reactance. Okay. So this is the reactance created by the capacitor. So normally this is referred as capacitive reactance. Capacitive reactance. Okay. So you need to remember this term. Capacitive reactance. Okay. Capacitive reactance. Capacitive reactance. So what is the capacitive reactance? That is 1 over C omega J. If you want to get this J up, what you have to do? If you want to get this J up, what you have to do? Maybe you can remember that. This part also we have to multiply it by J. This one also multiplied by J. Then J into J, what is the value? J into J, what is? J is -1 square. Then J into J, what is? -1 square root multiplied by -1 square root. What is that? -1. No? J into J, it will be -1. So this will be minus, then minus J C omega. Same 1 over C omega J. Okay. So this is the capacitive reactance. This is the capacitive reactance. The resistance created by the capacitor. Okay. Okay. Now if you consider a inductor, if you consider the inductor, the inductor is also work as a capacitor. Okay. Inductor and capacitor both are energy stored device. Okay. Capacitor and inductor are both energy stored device. Okay. So because of this energy stored, normally the voltage and currents are not in same phase. If you get this time domain current and voltage, those are not in same phase. Okay. Those are in different phase. That is why we have this kind of complex resistance or reactance. Okay. It is just for your knowledge. Okay. No need to pay you much attention on that. Okay. So anyway, okay, if you consider the inductor, the same things you can see. If you consider the inductor, the same thing you can see, but it is the vice versa of the capacitor. Okay, vice versa means this is the voltage curve of the capacitor. No? Okay, this is the voltage curve of the capacitor, and for the inductor, the same type of current curve you will get. Okay, okay. So I will write it here. Okay, and if you consider the capacitor. Okay, if you consider the capacitor, if I did here, if you consider the capacitor, okay, so you know that this is the voltage curve of the capacitor. V. This is called steady state. This is called transient state. Transient state. This is the voltage. Current curve is like this. At the steady state, current is 0. At the transient state, current is decreasing. Like this. This is a current. And if you consider the inductor, same kind of graph you will get like this. But this is not for the voltage, this is for the current of the inductor. This is the current of the inductor. Same way, this is the steady state, this is the transient state. Okay. And the voltage curve, will be like this. Okay. Okay, will be like this for the capacitor. Okay, for the inductor. Okay, so capacitor is equal to Q divided by V. Okay, and sorry, that equation is there. PT is equal to 1 over C integration of IT dt V naught. Okay, and IT is equal to C dVT. Okay. The same type of equation you will get here also. For the VT, you will have L dIT dt. Okay, this L is the inductance. This L is the inductance measured in Henry. This is measured in Henry. Okay. Okay. And there is the same type of equation for the current also. For the inductor, same type of equation for the current also. Okay. 1 over L integration of VT dt plus some I naught, some I naught, something like this. Okay. So here VT 1 over C IT dt plus V naught. Here IT 1 over L VT dt plus I naught. Okay. Maybe this is not 100% correct. Okay. And just I write as I can remember. If you want to verify these equations are correct, please check the internet. Okay. Please check the internet. Okay. Or maybe I have some notes and I will upload them to the LMS. Okay, then you can refer. Okay, but we are not no need these things. Okay, this is just for understanding. And if you in the same manner, if you consider this this equation, it is easy to use this equation. Okay, for an inductor. Okay, and if we do the in the same manner, if we do the what is that? Domain transformation. If VT is domain transfer onto V for the frequency domain, that is V omega using Fourier transform, and L is there. If IT is Fourier transform, if we get the Fourier transform of IT, let's say that I omega, okay. Now you have to get the derivation of I omega. So you will have J omega here. Okay. J omega here, like this. Okay. in the same manner, you can write V omega divided by I omega, then you will have Lj omega. Then what is this? What is this? This is also the resistance created by a inductor. Okay, but it is an imaginary one. J is there. It is an imaginary or complex value, complex resistance. This is measured in ohm, okay, but it is a complex resistance. So normally we use reactance word here also, reactance, but this will be a inductive reactance. Inductive reactance. Okay. So this is what you need to keep in mind. Okay. Then if you consider the capacitor, capacitive reactance is capacitive reactance is 1 over C omega J. Okay, this C is measured in farad. This omega is the, so we are now considering frequency domain. This V omega is a frequency domain, and if V is changing, this omega is considered as the frequency. Okay, so this is the frequency of the signal that is in. So this omega is actually angular frequency. So you need to know these things also for the measurement. We will see them later when we are, as I told you, we have to get we have to learn the time domain and frequency domain signal measurement. Okay. So you have to do some sine signal measurement, sinusoidal signal measurement. Okay. For a sinusoidal signal, this omega, okay, that is we normally referred as angular frequency. Actually, that is angular velocity. Okay, it is angular velocity, but normally referred as angular frequency, omega. Okay, and this is equal to 2πf. Okay, this f is the frequency. F is the frequency measured in hertz. Okay, so this omega is measured in radian per second. Okay, radian per second. This is very important. You have to remember this. Okay, omega is the angular frequency or angular velocity measured in radian per second, and it is equal to 2πf. F is the normal frequency measured in hertz. Okay, this is measured in radian per second. Okay, so this omega is the frequency measured in radian per second, and this J is the complex value. Okay, so that is 1 over C omega J. That is the capacitive reactance. Okay, and for the inductive reactance is L omega J. Okay, this is also measured in ohm. This L is measured in Henry, and this omega measured in radian per second. This is J. Okay, so the total value is measured in omega, Henry into radian per second. Okay, so this is the capacitive reactance, and this is the inductive reactance. So that is what you need to know. Okay, now another point. Tell me, if we have connected two resistances series, what is the equivalent resistance? What is the equivalent resistance? What is the equivalent resistance here?
R1 plus R.
Yes, R1 plus R2. That is the equivalent resistance. Okay. And if you parallelly connected R1, R2, what will be the equivalent resistance? Then 1 over R, this R is the equivalent resistance, is equal to 1 over R1 plus 1 over R2. Okay. Now let's say that you have connected the inductor, resistor and the inductor. Let's say that inductor has a inductor is L, this resistance is R. Okay. So what is the equivalent resistor here? This R is the resistance of the resistor. Okay. The resistance of the inductor is what is? L omega J. No? L omega J. This is the reactance. Okay. This is the inductive reactance. Okay. Then what is the total equivalent resistance?
R plus L omega.
Yes, R plus L omega J. This is the equivalent resistance. Equivalent resistance. But or total resistance. But you can see that this is also a complex value because J is there. Okay. So this is normally not referred as resistance. We normally refer it as impedance. This is the impedance. Okay. So this is the impedance. Okay. This is the impedance, resistance plus inductive reactance. Okay. So that is the impedance. Okay. And if you have this kind of one, if you connect a resistor with respect to capacitor, what is the impedance? What is the total impedance of this circuit? Let's say that this is C. Then what is the total impedance? This impedance is R plus this impedance is yes 1 over C omega J. Okay. So now if we have a inductor with respect to resistor, okay, parallelly connected. Let's say that this is L and this is R. Maybe you can try to find the impedance here. Okay. In the same way, if we connect a capacitor parallelly with the resistor, here also maybe you can find the total impedance. Okay. Try to find this one and this one. Okay. So actually you need this knowledge. For the AC bridge analysis, you should have this basic knowledge. Okay. So if we have this basic knowledge, we can do further. Okay. So this basic knowledge you should have. Okay. Okay. Now we are talking about AC bridge actually. AC bridge. As I told you, there are several type of AC bridges. Okay. For example, I will take the book. Okay, that is fine, I think. Here inductor, this is the present. This is actually made by Kaldesh. Okay, this is the equation. Okay, this is the equation for IT. Same, you know. I think I have correctly written. This is for the current of the inductor. Okay, and this is the voltage of the inductor. Okay, I have correctly right. Okay, so that is correct. Okay, the equation I have for the inductor current, this equation is correct. Okay, 1 over L like this. Okay, so here the inductor is starting to charge at T0. Okay, so up to T0, it is a used inductor. That means it has an initial charge. That means initial current. Okay. Okay, this is the book, and the bridges are in 11th chapter. We started from chapter 11. Okay, so we have talked about the Winston Bridge. Try to do some example here. Okay, so you can do some example, one or two example. I have already uploaded this book. Okay, so try to do the examples. If you have any problem, you can ask me. Okay, then AC bridge. Okay, AC bridge. There are several type of AC bridge. Okay, so we will start from here maybe. Okay, the whole has the same principle. Okay, so I will take this one, Maxwell bridge. Okay, so this is the Maxwell bridge. This is normally referred as Maxwell bridge. Okay, now you can see that this is a variable resistor. This one also variable resistor, and these are known resistance and known capacitance, and this Rx means unknown inductance and capacitance. So, okay, now what you need to do is, okay, find the total impedance here. Normally impedances are marked using Z. Okay, total impedance here. Okay, normally reactance are masked in X. Okay, if it is a capacitive reactance, normally it is Xc. Inductive reactance is Xa. Okay, so R plus Xc. Okay, normally referred as impedance, that is Z. We are using Z. Okay, so you have to find this Z1, the total impedance here, total impedance here, Z2, total impedance here, Z3, total impedance here, Z2. Okay, so the total impedance Z2 is equal to R2, Z3 is equal to R3. What is Z4? What is Z4? If this source has omega frequency, that is Rx plus J omega L. No? This is the impedance Z4. In the same manner, try to find the impedance of Z1. Okay, and at the balance condition means the zero is there. The balance condition, same what is called same relation is there. Okay, at the balance condition, Z1 divided by Z3 is equal to Z2 divided by Z4. Okay, so this is the balance condition. So now try to find this Z1. Okay, try to find this Z1. Okay, actually Z1 is to find the Z1 is very easy. 1 over Z1 is equal to 1 over R1 plus 1 over C omega J. That means C omega J will go up. Okay, so here you can find the Z1 also. Okay, so you have this uh, you have this relation. Okay, so you can find the Z1, Z3 already there, Z2, Z4 you can find. Okay, then okay, so this is Y1 means 1 over Z1. 1 over Z1 is normally referred as Y1. Y1 normally is called admittance. Admittance, no? Maybe you can remember. The Y1 is referred as admittance. 1 over impedance. That is normally referred as admittance. Okay. So I will do it. Okay. Maybe you can understand. Okay? If you see this, you can understand. I will do it. I think it is better. Okay. Okay, so this is the Maxwell bridge now. This is the Maxwell bridge. Okay, so Z1 1 over Z1 is equal to 1 over R1 plus 1 over 1 over C omega j. Okay, so here that is 1 over C omega j. No? Okay, so it will be 1 over 1 over C omega j. So it will be C omega j. Then you can find the Z1. Z1 is equal to here you can get the common denominator. Then R1 once it go up, it will be R1 divided by R1. Sorry. 1 plus j omega R1 is also there, j omega R1c. Okay, so this is Z1. Okay, so you can write that expression Z1 divided by Z3 is equal to Z2 divided by Z4. Okay, so Z1 is this one, R1 1 over j omega R1c. Okay, and Z3 is R3. This is divided by R3. Okay, this is divided by R3. That means multiplied by 1 over R3. So it will be R3 here. Okay, and it is equal to R2 divided by Rx plus j omega Lx. Okay, so this is you have. Okay, this is you have. Okay. Okay. Then I will take this one here. Okay. Then I will have Rx plus j omega Lx. These are the unknown variable, Rx and Rx, unknown terms. Okay. Unknown terms, Rx and Lx. Okay. And I will take all known terms here in this side. Okay. So I will have R2, R3 divided by R1. Okay. And this one, 1 plus j omega R1c. Okay. Then I can expand this. I will have R2, R3, R1. Okay. R1 plus R1 cancel. I will have j omega c R2, R3. R2. Here I have Rx plus j omega Lx. Then how can we find Rx and Lx? How can we find Rx and Lx? Using this equation, how can we find? Using this equation, how can we find Rx and how we can find? Using this equation, how we can find? This is Rx, j omega Lx. Okay. Actually, using this equation, we can find. Okay. So this is a complex equation. Okay. So if this part is equal to this part, that means this is the real part, this is the real part, and this is the imaginary. Okay. And this is the real part of this side, and this is the real part of this side, imaginary part of this side. Okay. To have this equation, to have this equate, okay, real part should be equal. Real part should be equal to each other, should be equal, and imaginary part also should be equal to each other. Okay, so that means here Rx, that is the real part. Okay, so Rx is equal to this real part, R2, R3, R4. Then you can find the unknown Rx. Okay, same manner, this imaginary part you can equal to this imaginary. Okay, so j omega Lx is equal to j omega C R2 R3. Okay, okay, so j omega cancel out, then you can find Lx as C R2 R3. Okay, so now you can see that you can find the unknown Rx and unknown Lx, resistor value and the capacitor value. Okay, okay, so the same thing is doing here. Okay, they get this one. Okay, then they equal imaginary parts and real part. Okay, so Rx is this one, R2 R3 divided by R1, R2 R3 divided by R1, R2 R3 divided by R1, R2 R3 divided by R4. Sorry, this is R1. Okay, this is R1. There is no, this is R1. Okay, so here R1, R2 R3 divided by R1. Okay, then Lx is equal to C1 R2 R3. C1 is this one, C1 R2 R3. C1 R2 R3. Okay, we have for C1 we have put as C. Okay, so this should be C1. C1 R2 R3. Okay, so maybe you understand how we can find Rx and Lx. Okay, so that is what you need to know. Okay, now I will give you one homework. Okay, okay, now tell me, if we apply a capacitor here, so you have to do this at home. Okay, so this kind of question will come. Okay, if you apply a capacitor here, Cx, okay, instead of this Lx. Okay, can we find the capacitance value? Can we find the Cx value using this setup? That is my first question. Okay, if not, that means if we can't estimate the Cx, how we can modify this setup to measure unknown capacitance Cx. Okay, so that is my two questions. Okay, so try to do it at home. The same kind of question will come to your exam also. Okay, so you should be able to solve this kind of one. Okay, so try to do this one. Okay, okay, so we will stop here. Okay, so keep remember my question. Okay, in next week I will ask.
We have to modify the setup of if we cannot find the capacitance.
Yeah.
We have to modify the setup. No?
Yeah, okay. First check if we put the capacitance here instead of inductor, whether we can measure the Cx using this setup. If we can't measure, then try to modify this setup to measure the Cx. That is what we will do. Okay. Okay.
Okay.
So we will stop here. Okay. And if you have any problem, you can ask. Otherwise, you can leave.
Okay, so